Hey everyone, welcome to our presentation for the final project for ICE 609 Mathematical Modeling. I'm Justin Hink, and my partner for this project was Dittenhafer. He'll be around for the second part of the presentation to talk about the results that we gathered and some of the conclusions that we've drawn. So the agenda for today's presentation, or talk today, is going to be about the problem that we're tackling, or sort of our high-level methodology of how we're going to attack the problem. I'll get into a few of the details to go into the models and some of the actual code that we use to tackle the problem. And then, as I mentioned before, Dan will be around to talk about the findings that we came up with. So for the analysis of the problem, we want to make some investment decisions in the market. I mean, this is a famously hard problem. It's been studied by many people, probably smarter than us, but we thought we'd give it a shot. What we're trying to do here is predict future price movements, and from that make some trading decisions. So because this is a mathematical modeling course, we're going to use some algorithms to do this. So from a high level, the mathematical models that we have incorporated into our trading strategy here are something based on the fast Fourier transform with a low-pass filter attached to that, Monte Carlo simulation, something very similar to what we took in Andrew Hernandez's advanced programming techniques course last year. And then sort of on the tail end of both of those, we've attached a model that we derived from the Kelly criterion, which we use to basically make decisions on how much we should bet, how much we should allocate to our positions in the market. So I guess we could break that down further into three main steps. We want to model a stock's true price in the market. We want to compare that to what the market is actually telling us the price is. And if there's a gap there, we want to make a buy, sell, or even short position decision based on that result. So here's sort of a block diagram of that. We got to take in some historical market data. We apply two different algorithms. See, these don't run at the same time. There was actually two different models that we're testing out in our project. And then both of them use the same sort of second step, which is the Kelly criterion position sizer. And then from that, we make a decision whether to make a trade or not. So the first model that we talked about, or that we incorporated rather into our project, is the fast Fourier transform. What that does is it transforms a time series signal into something in the frequency domain. This is a technique that is very prominent in the electrical engineering and signal processing worlds, and anyone that's taken an electrical engineering undergrad would be very familiar with this technique. Quick example of that, so we have a time series signal here, basically comprised of two sine waves of two different frequencies. We transform that and we see something that looks very different and very easy to analyze. We have two spikes at 50 Hertz, which is one of the frequencies here, and 80 Hertz, which is the other frequency here. Add on that low-pass filter, which basically smooths the signal out. It's a signal processing technique that is very easy to do in the frequency domain. So once we have transformed the signal to something that has those nice little spikes that we just saw, it's very easy to apply a low-pass filter to it. So overall, our fast Fourier transform trading thesis is a stock chart is just a time series signal. It looks noisy. If we filter out some of that noise, maybe we have a better idea of what the stock's true price is. So here's an example of a smoothed out signal, smoothed out stock price time series. The green here is the actual market data throughout history, and then the smooth blue line here is what we see as our model output. So basically a smooth version of the stock throughout time. So here's some quick code to show how we did that. We used SciPy's built-in Fourier transform libraries that were very handy. So that's what we're doing here with this FFT call and this inverse FFT call at the end, which is essentially taking the three steps here. We transform it into the frequency domain, do some analysis, and then transform it back after we filter it back to the time domain so we can make trading decisions off of it. The high-pass filter code is very, very simple. In the frequency domain, as I mentioned, it's basically just an if-else statement. We have, like I said, it's basically 5 lines of code. Computationally, it's much simpler as well. It goes from being an ON squared algorithm to n log n in the frequency domain. So for the Monte Carlo simulation, we have it's our second approach to making these trading decisions. We take price differences from the past 10 days, fit them to a normal distribution, and then predict the next day's possible outcomes based off of that. So here's a bit of code that does that. It's pretty similar to what we've done in the past. Basically, just making a decision based off a quick little simulation that we've done to see what could happen tomorrow based on past results. So both these algorithms hopefully will give us a price gap between what the market tells us the price is and what we've modeled the theoretical true price to be. So that represents an edge, hopefully. So with that edge in hand, what do we do? What do we do in terms of making a decision? Should we buy? Should we sell? Should we hold? Should we short? And that's where the last model comes in. And that's called, and that's using something called the Kelly criterion. So the Kelly criterion is a technique to maximize growth by balancing a portfolio properly. We're not the first ones to do this. This was incorporated first by blackjack players, actually, to maximize their bets based on their card counting edge that they would get in a casino. One of these players, Ed Thorpe, brought the technique into the actual stock market in the 1970s, and he made a lot of money. So we're basically piggybacking off of what his pioneering work and trying to use it for our purposes here. So it's actually a really complex problem when you have multiple stocks in your portfolio. It turns into a quadratic programming mess, but something that we're not going to tackle. But for our situation, we just have one stock and cash in our portfolio at any given time, and because of that, it simplifies dramatically to this simple algebraic equation where f star is our fraction of our portfolio that we're going to allocate to a bet or to our stock in the market. So if we have $1 million of value in our portfolio and f star comes out to be 0.6, then we allocate 60% of our capital to the stock and the other 40% cash. P is the probability of us winning our bet, or in our case, the price movement going in the way that we think that it will. And B are our net odds, and that's directly proportional to the size of the price gap. So with that, I'm going to hand it over to Daniel, and he's going to talk about the results and see if we actually came up with something that is worth using.
Thanks, Justin. Hi, my name is Daniel Dittenhafer. In order to test our models, we ran each through a series of tests. Each test started with $100,000 on January 1st, 2010, and ran for 4 years. We selected 9 corporate stocks and an index based on the S&P 500. This is an example of the Monte Carlo model through one of its tests. The Fourier transform had similar visuals. The top chart shows the change in portfolio value through the course of the test, and the bottom chart shows the actual and predicted prices, though it's difficult to see given the scale. A raw output from the models is shown here. Each row represents a security and the ending portfolio value from each model. This chart helps to illustrate the differences, and in some cases the models perform similarly, while in others it seems the Fourier transform is performing better. This chart shows the annualized returns by security. Again, it seems the Monte Carlo model is not performing as well as the Fourier. Looking at summary statistics, we see the Fourier transform has a higher median and mean, but also has a higher standard deviation as compared to the Monte Carlo approach. We decided to run a series of statistical hypothesis tests to measure in a more stringent manner how well the models were performing. To begin with, we have a hypothesis test with a null hypothesis that the model's outcome is the same as doing nothing, starting at 100,000, ending at 100,000, with the alternative being that the model produces a better outcome, i.e. we make money. So we'll begin with the Fourier transform, and we check for nearly normal distribution. Although not great, we accept that this is nearly normal and move forward with the test. We found the t-score to be approximately 1.38 with a p-value of approximately 0.0998. As such, we accepted the null hypothesis and concluded the Fourier transform is not performing significantly better than doing nothing. Next up, we perform the same hypothesis test against the Monte Carlo model. Again, the distribution is not purely normal, but also close enough for our purposes. Working through the hypothesis test, we see the t-score is approximately negative 0.47, and the p-value is approximately 0.67. Again, we accepted the null hypothesis and concluded the Monte Carlo model is not significantly better than doing nothing. Our last hypothesis test was a difference of means test. We wanted to see if there was a significant difference between the results of the two models. Specifically, was the Fourier transform doing better than the Monte Carlo simulation? A bit surprisingly, we found the t-score was 1.35 with a p-value of approximately 0.10. Basically, the Fourier transform was not significantly better than the Monte Carlo simulation, and we did not reject the null hypothesis. In the end, our models, as implemented in this project, seem to offer no significant gain in the market. Any gains or losses we saw in the tests were just as likely from chance as the models. We have high hopes that tuning and refining the models could yield better results. Maybe even combining them in some way could be beneficial. But we'll need to leave that for a different exercise. Thank you for your time. If you have any questions, please don't hesitate to contact us. We welcome comments through the comment section as well. Thank you.